Gravity. It's something we all experience every day. But have you ever wondered how it works? Isaac Newton first developed a theory to describe gravity in the 17th century, and this theory has since been associated with an incident where he observed an apple falling from a tree. He realized that there was a force pulling the apple down towards the earth. This force he called gravity. But gravity is not just limited to apples. It's the force that keeps the moon orbiting around the Earth and the planets orbiting around the sun. It is also responsible for keeping us and everything on Earth grounded. According to Newton, gravity is a force of attraction between two masses. The strength of this force depends on the masses of the objects and the distance between them. The greater the masses, the stronger the gravitational pull. And the closer the objects, the stronger the gravitational force. This is nicely summarized in this equation for calculating the magnitude of this force. This equation resembles what is known as an inverse square law, meaning that if the distance between two masses is doubled, then the gravitational force between them falls down to a quarter of the initial value. On Earth, gravity gives weight to all physical objects and causes them to fall towards the ground when dropped. This is why, when you jump, you come back down. Another quantity associated with gravity is the gravitational field strength, which is defined as the gravitational force exerted per unit mass in a gravitational field. For a small mass in the field of a celestial body, the field strength is calculated as follows, and as the equation shows, it follows the inverse square law as well. On the Earth's surface, this value is 9.8 newtons per kilogram. From Newton's second law of motion, force per unit mass is defined as acceleration of a body. Thus, gravitational field strength can also be called acceleration due to gravity. All objects near the Earth's surface fall down with an acceleration equivalent to 9.8 meters per second squared. In general, the acceleration due to gravity in any field is the same for all matter. That is why, for instance, a hammer and a feather will fall at the exact same rate when dropped in a vacuum, where there is no air resistance. In orbit, which is at a greater distance from the Earth's center, there is very weak gravity, and astronauts appear to float. This is because they are in a state of free fall around the Earth, constantly falling towards it, but never quite reaching it, due to their tangential velocity, which causes them to orbit around the Earth instead. Any two masses with a gravitational influence on each other can be regarded as a system. Take an Earth-rock system, for instance. This system has a potential energy associated with it, and when it converts to kinetic energy, most of it manifests on the rock, which is the smaller mass. So, for simplicity, the rock is said to possess gravitational potential energy inside the Earth's field. This potential energy increases with the rock's distance from the Earth's center. Near the Earth's surface, where the Earth's gravitational field is uniform, the potential energy is measured relative to the ground and is proportional to the height of the object above the ground. As we move away from the Earth's surface, the field loses its uniformity, and now the gravitational potential energy has to be measured relative to some imaginary point that is infinitely far from the Earth, such that the gravitational field is zero at that point. At this point, often called infinity, gravitational potential, which is potential energy per unit mass, is defined to be zero and negative anywhere else inside the field. This does not mean an object inside the field really possesses negative energy, but it simply means that its energy is below that of an object at infinity, and also shows that work has to be done on said object to push it back to infinity. Although Newton's theory predicts the behavior of gravity fields perfectly, it provides no explanation on what gravity exactly is and what causes it. In 1915, Albert Einstein came up with a new theory of gravity, known as general relativity. This theory provides a geometric definition of gravity, in which gravity itself is simply a curvature or an indentation in space-time, which affects how objects move. Space-time is the fabric of the cosmos, in which everything else exists. It is flexible. thus can stretch, bend, and twist. Matter causes space-time to curve around it, creating a gravity well in which other masses tend to fall into, and this is what we experience as gravity. Our brains cannot conjure up this curvature, but we can illustrate it on a 2D surface that curves into a third dimension. So, masses do not attract each other, but simply follow the curvature of space-time around other masses. The bigger a body is, the greater the curvature it creates in space-time, and hence the greater is its influence on other objects. We call this a stronger gravity. General relativity predicts phenomena such as gravitational lensing, which is the bending of light rays as they travel past a massive object and follow the curvature of space-time that it creates. This phenomenon allows us to see, for instance, an object directly behind the Sun during a solar eclipse. General relativity also predicted other phenomena before they were observed. These include black holes, gravitational waves, and different clock rates at different points in a gravitational field. Although Newton's theory of universal gravitation does not shed light on the nature of gravity, it still works perfectly in predicting how objects behave in gravitational fields and is thus quite useful in space travel and astronomy. That's it for the fundamentals of gravity. Thank you for watching.